Greetings, my beloved. Here we go again with a cosmic science lesson. With these lessons being learned by you, you are most certainly guaranteed to know more about the creation and the structure of all the universes than any of the so-called doctors of astrophysics in Western civilization. I say this with authority because from studying the theories and information they have, I know they do not know anything whatsoever about this creation from what we call, in my school of cosmic science, prime creator.
All elements, all matter in the universe could well have been the product of a primal transformation of their own. But how did this process work, and why in radium was it accompanied by the release of radioactive energy? In fact, the answer had been found years earlier. In 1905, an extraordinary revelation would forever change the way we look at the universe. Among the claims of Albert Einstein's theory of relativity was a single elegant equation, E equals mc squared.
One of the major questions in cosmology and in astrophysics is how the chemical elements came to be in the universe.
The E stands for energy, the M for matter, C is the speed of light. According to Einstein, just as heat and light are different forms of energy, so is matter itself.
So energy is never lost, or in fact gained. It's just transformed from one form into another. You can't actually prove that mass can be completely converted into energy using special relativity, but Einstein made that conceptual leap and conjectured that that was in fact true.
Einstein imagined matter as something like a battery, a form of stored energy. The concept was powerful, but could it be proven, and would it explain the origin of the universe? Rutherford decided to delve deeper by peering within the building block of matter itself, the atom. But a mathematician named Paul Dirac went one theoretical step further.
Paul Dirac held the Lucasian Chair of Mathematics in Cambridge, which was once held by Newton and is currently held by Stephen Hawking.
Dirac's theory was altogether counterintuitive. He argued that for Einstein's theory to be right, energy wouldn't just produce matter. It also had to generate a perfect mirror image, antimatter. Every particle has a twin, an antiparticle. If ever the two met, they would unleash a fury.
The special quality that antimatter has is that it can completely annihilate with matter to form energy.
Today, in colossal subterranean accelerators, the violent birth of matter and antimatter reveals the very traces of creation.
You may think that this is some sort of beautiful art, and it is in a sense art, but it's an art made by physicists. What you have is a big snapshot that captures in one moment all these dance of particles being created and destroyed inside particle accelerators. So it may look like Jackson Pollock, but it's actually a computer-enhanced picture of a particle collision within a detector. Each one of these particles, in a sense, tells the story, or a possible story, of how the universe was a long, long time ago.
The cryptic patterns of crashing particles is nature's own calligraphy. They are a scripted chronicle for how matter was formed in the Big Bang. So
So here you have a detail of what people would see in a detector, in which you have the debris of a little bang creating matter and antimatter out of energy. And this is a photon, and a photon is a little bundle of energy that doesn't leave a track because it doesn't have an electric charge. So it moves up here, it collides with a particle, and out of the strength of this collision, you have these two spirals coming out, one of them being a particle, which is matter, and the other one being its antimatter cousin, its antiparticle. And out of this collision, you have two tracks, this one that you can see, and then you have another one, which is an invisible one, which is another photon, a bundle of energy. And you can see precisely that this bundle of energy will eventually create matter and antimatter. And this happens at this point quite suddenly when this photon gives birth, in a sense, to an electron and a positron. And that is a beautiful manifestation of matter being created out of energy. Well, if matter and antimatter are essentially the same with opposite electric charges, where is the antimatter? How come the universe is made of matter? We go back to the laws that control how particles and antiparticles interact. And those laws show that the universe is not perfectly symmetric between matter and antimatter. Of course, all these pictures that we scientists build are very much dependent on our trust of the laws of physics. I mean, why should the pictures that we build of the universe really correspond to reality or not? Or how could we trust those pictures? Well, I think the best way to explain that is just to look at technology. As the universe cools and expands, the particles stop colliding so strongly and so energetically, and they have more time to look at each other and perhaps bind and do something. So at about 1 second of life, the universe started to make nuclei. That is, protons and neutrons started to bind. At about 300,000 years or so, atoms form, which means that the nuclei bind with electrons to form the atoms. Most of them, overwhelming majority, hydrogen. From those hydrogen atoms, they, because of gravity, form clouds. Those clouds start condensing. And they get denser and denser and hotter and hotter. And as that happens, those clouds start forming galaxies and stars within these galaxies, which are basically 99% of hydrogen burning. And eventually those stars are going to have solar systems attached to them. That is, they're going to have planets orbiting around them, and maybe you're going to have a planet which is close enough so that it's hot, but not too far enough so that it's not too cold, that life, as we understand it here on Earth, could develop. And then we could come back here and tell the story about the life of the universe from scratch to the end.
There's this impression that everything the scientists do is very circumscribed, whereas it is not, because we are bringing the ways in which we perform a model, the ways, the ingredients that we put in, and the ways in which we choose to mix the ingredients has a lot to do with our individual creativity and our feelings and our sense and intuition of how things ought to be. So it's almost like writing poetry, where you pick a particular poetic form. For instance, you could pick the sonnet, or you could pick the Japanese haiku, which each of these forms has a set of rules. So you operate within a set of rules, which is very much like the laws of physics that you operate within in a model. But then inside the form or inside the model, there's a lot of freedom. There's a lot of choices you can make.
Natarajan grew up in India. Her life changed when she was awarded a scholarship to Cambridge University in Britain. Here she's taken on a quest as spiritual as it is scientific. She ponders, the ultimate destiny of the universe.
We see the stars that shine in the galaxy, and we also have evidence that there's some gas in the galaxy, because we can see the light that's scattered off the gas. But as it turns out, galaxies contain a lot more than just that.
Natarajan owes her inspiration to a maverick astronomer named Vera Rubin, who in the late 1960s dared question a basic premise of astronomy.
What Vera Rubin did in her work was map the speeds of stars at different distances from the center of a huge spiral galaxy.
Vera Rubin noticed something which defied accepted wisdom. Stars spinning around the center of galaxies were supposed to behave like the planets that orbit the sun. They don't.
With our solar system, you have the sun in the center and you have sort of the planets orbiting around. And since the dominant gravity is that of the sun, the planets that are the outer planets, they move much slower than the planets on the inside. So naturally what people expected to find was similarly in a galaxy. If you measured the speeds of the stars away from the center towards the edge, you expected to fall off. And what Vera Rubin found instead, when she actually measured that for a spiral galaxy, was that the speed stayed the same. As she sort of mapped the speed of the stars from the inside out all the way out to the edge, they stayed the same.
Rubin was the first to pose a question that has baffled scientists ever since. If all the stars in a galaxy move at the same speed, regardless of their distance from the center, then the center couldn't be the only source of gravity affecting them. Something else would have to be exerting a powerful force. Something we simply can't see.
What she found was that in order to explain the speeds that she observed, she needed to have a lot more stuff in the galaxy than we see. And since the stuff is not visible and it's not emitting any light, she coined the term dark matter to refer to that.
Rubin had every reason to believe her discovery would be met with great excitement. It was, though not the kind she might have expected.
Her announcement that there was dark matter associated with every individual galaxy was received with much skepticism because of the far-reaching implications it had and because also of the inferred percentage of dark matter. From her work, she inferred that almost 90% of the mass in a spiral galaxy had to be dark.
Rubin's findings suggested that the destiny of galaxies is governed by a vast and inscrutable network. Every galaxy is enveloped in dark matter, invisibly locking all the stars in its embrace with the gravity it exerts. The black emptiness of space, it seems, isn't that empty after all. 99% of the universe could well be made up of dark matter, a sprawling cosmic web.
For cosmologists like myself, it's crucial to know precisely how much dark matter there is, in order to know what will become of the universe, eventually.
The total mass of our universe is what decides the fate of our universe, whether we continue expanding or whether we